Hello there, and welcome to Science with Sleepy. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight, we're going to explore something truly amazing. We're going to imagine what it would be like to build a house on a comet. Now, you might be thinking, comets are just icy rocks floating through space. They're small, they're cold, they're far away. How could anyone build a house there? Comets are more interesting than you might think. They're ancient, they're mysterious, and they hold secrets about how our solar system began. You'll hear about comets that have traveled billions of miles. You'll learn about their icy surfaces and rocky cores. You'll discover what happens when they get close to the sun. And you'll imagine what it would be like to live on one of these cosmic travelers, floating through space, watching the stars drift by. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now, let's begin. Chapter 1. What is a comet? The cosmic snowballs. A comet is like a cosmic snowball. Imagine a ball of ice and rock floating through space. It's so much more than that. These are ancient travelers drifting through the solar system for billions of years. Some of them are older than the planets themselves. They carry secrets from the very beginning of our solar system. Mostly, comets are made of ice. Water ice, yes, but also other kinds. Carbon dioxide ice, methane ice, ammonia ice. Picture these ices frozen solid because space is so cold. Far from the sun, temperatures can drop to minus 400 degrees Fahrenheit. That's cold, really cold. Cold enough to freeze almost anything. The composition of comets is fascinating. About 80% of a comet's nucleus is water ice. The rest, a mixture of frozen gases and rocky material. Carbon monoxide makes up about 10 to 20% of the volatile material. Methane and ammonia are also present in smaller amounts. When comets approach the sun, these frozen gases create spectacular tails. Research has revealed that comets also contain hydrogen cyanide, formaldehyde, and even alcohol. Comet Lovejoy, which passed close to the sun in 2015, was releasing alcohol at a rate that would fill 500 bottles of wine every second. That's a lot of alcohol, but you definitely wouldn't want to drink it. It's mixed with other chemicals that would be deadly. Scientists have been studying comet composition for decades, and the Rosetta mission gave us the most detailed look yet. When researchers analyzed data from Comet 67P, they discovered something surprising about the ice. The water ice in comets isn't pure. It's mixed with other frozen gases in a way that creates what scientists call a clathrate hydrate structure. This means the water molecules form a cage-like structure that traps other gases inside. It's like a cosmic ice prison for gas molecules. This structure is important because it affects how the ice behaves when it heats up. Instead of all the ice melting at once, different gases escape at different temperatures, creating complex activity on the comet's surface.
But here's where things get interesting. Some researchers thought all comets would have similar compositions. But when scientists compared different comets, they found surprising differences. Comet 67P has more carbon dioxide than expected. Other comets have more methane. Some have almost no ammonia. This tells us that comets formed in different places in the early solar system, and they've been preserving those differences for billions of years. It's like each comet is a frozen snapshot of a different part of the early solar system. This variety makes comets even more valuable for scientists trying to understand how our solar system formed. But comets aren't just ice. They also contain rock and dust, tiny grains of rock, bits of carbon, traces of organic molecules, all mixed together like a cosmic snowball with dirt in it. Scientists call this mixture the comet nucleus. That's the solid center of the comet. The dust itself is made of silicates. These are minerals rich in silicon and oxygen, the same materials that make up rocks on Earth. But in comets, these silicates are mixed with ice. They form tiny grains, smaller than a grain of sand. When gas blows these grains away, they create the dust tail. When scientists studied dust from Comet Wild 2, they found something amazing. Some of the dust grains were made of materials that formed at temperatures over 2,000 degrees Fahrenheit. That's hotter than lava. This tells us that comet material traveled from near the Sun all the way out to the cold outer solar system, then came back again. It's like a cosmic journey that took billions of years. Complex organic molecules also exist in comets. These are carbon-based compounds. Some of them are similar to the molecules found in living things. When the Stardust mission collected samples from Comet Wild 2, scientists discovered something amazing. They found glycine, which is an amino acid. This is one of the building blocks of proteins. They also found more than 20 different amino acids in comet material. Some researchers think comets might have brought the building blocks of life to Earth billions of years ago. The discovery of amino acids in comets was a huge surprise. Amino acids are the building blocks of proteins, which are essential for life. Finding them in comets suggests that the basic ingredients for life might be common throughout the solar system. Scientists have now found amino acids in several comets and asteroids. This tells us that these molecules formed in space billions of years ago, before life even existed on Earth. Some researchers think that comets might have delivered these molecules to Earth, helping life get started. It's like comets were cosmic delivery trucks, bringing the ingredients for life to our planet. But here's an interesting debate. Some scientists think comets brought most of the organic molecules to Earth. Others think Earth already had organic molecules when it formed. The truth is probably somewhere in between. But one thing is clear. Comets contain a lot of organic material. A single comet could have tons of organic molecules. If we could extract and use these molecules, they could be incredibly valuable. They could be used to make materials, to grow food, or even to create new compounds. But extracting them would be difficult, and we're still learning about what kinds of organic molecules comets contain. Every new mission teaches us something new. The nucleus is usually small. Most comet nuclei are only a few miles across. Some are smaller, some are bigger. The biggest ones might be 20 or 30 miles wide. But compared to planets, they're tiny. Earth is about 8,000 miles wide. A comet nucleus is like a pebble next to a beach ball.
When the Rosetta spacecraft studied Comet 67P, it discovered something fascinating. This comet is about 2.5 miles across at its widest point. It's shaped like a rubber duck, with a larger head and a smaller body connected by a narrow neck. This unusual shape reveals that comets can have complex structures. Researchers believe this shape might have formed when two smaller comets collided and stuck together billions of years ago.
The Rosetta mission spent 2 years studying this comet, taking thousands of pictures and collecting data that changed how we understand these cosmic objects. When scientists measured the comet's mass and volume, they discovered something surprising. They found it was much lighter than expected. The comet weighs about 10 billion tons. That sounds like a lot, but for something 2.5 miles across, it's incredibly light. If you could somehow bring the entire comet to Earth, it would weigh less than a small mountain. This low mass means the comet's gravity is incredibly weak. Scientists calculated that if you dropped a penny from waist height on Comet 67P, it would take about 2 minutes to hit the ground. On Earth, the same drop takes less than a second. This weak gravity is one of the biggest challenges for building anything on a comet. The Rosetta mission used a clever trick to measure the comet's mass. As the spacecraft orbited the comet, scientists watched how its path changed. The comet's gravity pulled on the spacecraft, changing its speed and direction slightly. By measuring these tiny changes, scientists could calculate the comet's mass. It's like weighing something by watching how it affects a satellite orbiting around it. The measurements were so precise that scientists could detect changes in the comet's mass as it lost material near the Sun. They watched the comet lose weight in real time, like watching someone on a cosmic diet. But here's something that surprised everyone. When scientists first calculated the comet's density, they expected it to be low, but not this low. The density measurements showed that Comet 67P is about 75% empty space. That's more porous than most sponges. Some researchers think the comet might be even more porous in its center, with the porosity increasing as you go deeper. This means the comet might be like a cosmic Russian nesting doll, with layers of increasingly porous material. The outer layers are more compact, but the inside might be almost completely empty. This structure would make the comet incredibly fragile. If you tried to dig into it, you might find that the material just crumbles away, like trying to dig into a pile of loosely packed snow. Now, here's something surprising. The density of comet nuclei is very low. Most comets have a density of about 0.6 grams per cubic centimeter. That's less than the density of water. Earth's density is about 5.5 grams per cubic centimeter. This low density means that comets are mostly empty space. They're like cosmic sponges, full of holes and gaps. When Rosetta measured Comet 67P's density, scientists found it was about 75% empty space. That means if you could squeeze all the empty space out of a comet, it would be much smaller. This is why comets are so fragile and can break apart easily. Scientists have been trying to understand why comets are so porous. One theory is that comets formed from tiny particles that stuck together very gently. In the early solar system, there wasn't much gravity to pack things tightly. So the particles just kind of stuck together loosely, like a cosmic snowball that was never really packed down. Over billions of years, these loose structures have stayed loose. The particles are held together by weak forces, like static electricity or the stickiness of ice. But these forces are so weak that the comet can break apart easily. Now, here's something surprising. The density of comet nuclei is very low. Most comets have a density of about 0.6 grams per cubic centimeter. That's less than the density of water. Earth's density is about 5.5 grams per cubic centimeter. This low density means that comets are mostly empty space. They're like cosmic sponges, full of holes and gaps. When Rosetta measured Comet 67P's density, scientists found it was about 75% empty space. That means if you could squeeze all the empty space out of a comet, it would be much smaller. Scientists have been trying to understand why comets are so porous. One theory is that comets formed from tiny particles that stuck together very gently. In the early solar system, there wasn't much gravity to pack things tightly. So the particles just kind of stuck together loosely, like a cosmic snowball that was never really packed down. Over billions of years, these loose structures have stayed loose. The particles are held together by weak forces, like static electricity or the stickiness of ice. But these forces are so weak that the comet can break apart easily.
Researchers have done experiments to understand comet structure. They've created models using tiny particles and watched how they stick together. They've found that the way particles stick together depends on their size, their shape, and what they're made of. Smaller particles stick together more easily, but they also create more porous structures. This matches what we see in comets. The particles that make up comets are probably very small, maybe just a few millimeters across. When billions of these tiny particles stick together, they create a structure that's mostly empty space. It's like building a house out of tiny Lego blocks, but only using a few blocks and leaving huge gaps between them. Interestingly, even though comet nuclei are small, they can have huge tails. When a comet gets close to the sun, the ice starts to change. Well, not exactly melt, it sublimates. That means it turns directly from ice into gas, skipping the liquid stage. The gas streams away from the comet, carrying dust with it. This creates the comet's tail. Measurements show how much material comets lose. When Comet 67P was closest to the Sun, it was losing about 1,000 pounds of material every second. That's like losing the weight of a small car every single second. Over the course of its 6.5-year orbit, the comet loses millions of tons of material. But here's the surprising part. Even though it loses so much material, the comet doesn't disappear. Evidence suggests Comet 67P has been orbiting the Sun for thousands of years, and it will probably keep going for thousands more. The comet is so large that even losing millions of tons doesn't make much of a difference. It's like a mountain losing a few grains of sand. You'd never notice. But if you were trying to build a house on the comet, you'd definitely notice. The ground beneath you would literally be disappearing bit by bit every second. A comet's tail can be millions of miles long. It can stretch across the sky. It can be visible from Earth, even though the nucleus is tiny. The tail is what makes comets beautiful. It's what makes them famous. When people see a comet, they're usually seeing the tail, not the nucleus itself. Comets come from two main places, the Kuiper Belt and the Oort cloud. First, the Kuiper Belt. It's a ring of icy objects beyond Neptune. It starts about 30 times farther from the Sun than Earth. It extends to about 50 times Earth's distance. Then there's the Oort cloud. It's much farther away. This is a spherical shell of icy objects that surrounds the entire solar system. It starts about 2,000 times farther from the Sun than Earth. It extends to maybe 100,000 times Earth's distance. That's really far away. Most comets stay in these distant regions. They orbit the Sun slowly, taking thousands or millions of years to complete one orbit. But sometimes something disturbs them. A passing star, a collision with another object, the gravity of a planet. When this happens, a comet might fall inward toward the Sun. It becomes a short-period comet or a long-period comet.
Scientists estimate there might be trillions of comets in the Oort cloud alone. That's more comets than there are grains of sand on all the beaches on Earth. Most of them will never come close to the Sun. They'll just drift in the darkness forever, carrying secrets we may never discover. Short-period comets take less than 200 years to orbit the Sun. They usually come from the Kuiper Belt. Halley's Comet is a famous short-period comet. It comes around every 76 years. The last time it was visible from Earth was in 1986. The next time will be in 2061. Long-period comets take more than 200 years to orbit the Sun. Some take thousands of years, some millions of years. They usually come from the Oort cloud. These comets are harder to predict. We don't always know when they'll return.
When a comet approaches the Sun, something amazing happens. It starts to heat up. The ice begins to sublimate. Gas streams away from the nucleus. This creates a cloud around the comet called the coma. The coma can be huge. It can be larger than planets. It's made of gas and dust streaming away from the nucleus. The coma is what makes the comet visible. It reflects sunlight. It glows. From Earth, it looks like a fuzzy star. But it's not a star. It's a cloud of gas and dust surrounding a tiny icy nucleus. The coma can be huge. Comet Holmes, which appeared in 2007, had a coma that was larger than the Sun itself. For a few weeks, it was the largest object in the solar system, even though its nucleus was only about 2 miles across. The coma was so big that if you could see it from the side, it would stretch from Earth to the Moon and back again. What's surprising is that even though the coma looks solid, it's actually incredibly thin. If you were floating inside a comet's coma, you wouldn't even notice it. The gas is so spread out that it's thinner than the best vacuum we can create on Earth. Scientists measured the density of Comet 67P's coma and found it had only about 1,000 molecules per cubic centimeter. That sounds like a lot, but Earth's atmosphere has billions of times more. You could float right through a comet's coma and barely feel anything. But the coma is still important. It's what makes comets visible from Earth. And it's what creates the beautiful tails we see in the sky. As the comet gets closer to the Sun, the solar wind pushes the gas away. This creates the tail. Actually, comets usually have 2 tails, the gas tail and the dust tail. The gas tail is made of ionized gas. It's blue. It points directly away from the Sun. The dust tail is made of tiny dust particles. It's yellow or white. It curves behind the comet. The tails can be incredibly long. Some comets have tails that stretch for hundreds of millions of miles. That's longer than the distance from Earth to the Sun. The Great Comet of 1843 had a tail that was more than 200 million miles long. That's more than twice the distance from Earth to the Sun. The tail is what makes comets so beautiful. It's what makes them so famous. What's interesting is that while the tail looks solid, it's actually mostly empty space. The particles are so spread out that if you were inside a comet's tail, you wouldn't even notice it. But the nucleus itself is dark, very dark. It reflects only about 3 to 5% of the sunlight that hits it. That's darker than coal. The surface is covered with dark material, carbon-rich compounds, organic molecules. This dark coating forms as the comet ages. As ice sublimates, the dark material is left behind. It builds up on the surface, making the comet darker and darker.
The nucleus is also irregular. It's not a perfect sphere. It's lumpy. It has hills and valleys, craters and cliffs. Some comets are shaped like peanuts. Some are shaped like potatoes. Some have two lobes connected by a narrow neck. When the Rosetta spacecraft visited Comet 67P, it discovered it looks like a rubber duck. It has a big head and a smaller body connected by a thin neck. The surface is also porous. It's full of holes, like a sponge. The ice is not solid. It's full of empty spaces. This makes comets very light. Their density is low. A cubic foot of comet material might weigh only a few pounds. That's much lighter than rock, much lighter than ice on Earth. This low density means that comets are fragile. They can break apart easily. If a comet gets too close to the sun, or if it passes too close to a planet, it might break into pieces. Some comets have been observed splitting in half. Some have broken into dozens of pieces. Scientists call this cometary fragmentation. Comets also rotate. They spin as they orbit the sun, but their rotation is often irregular. They might wobble, they might tumble. This is because they're not perfectly round. Their irregular shape causes their rotation to be unstable. Some comets rotate very slowly, taking days or weeks to complete one rotation. Others rotate quickly, completing a rotation in just a few hours. Comet 67P rotates once every 12.4 hours. As the comet gets closer to the sun and becomes more active, something interesting happens. Its rotation speed changes. The jets shooting out act like tiny rocket engines, speeding up or slowing down the comet's spin. Scientists watched Comet 67P's rotation speed up by about 20 minutes per orbit as it approached the sun. That's like a cosmic clock that runs faster and faster. The rotation affects how the comet heats up. The side facing the sun gets hot. The ice sublimates. Gas streams away. But as the comet rotates, different parts face the sun. This creates a complex pattern of heating and cooling. Some areas might be active, with lots of gas streaming out. Other areas might be quiet, with little activity. Comets also have jets. These are streams of gas and dust that shoot out from specific spots on the surface. They're like geysers, but instead of water, they shoot out gas and dust. The jets are caused by pockets of ice that heat up and sublimate. The gas escapes through cracks or holes in the surface, creating a jet. When Rosetta watched Comet 67P, it saw jets shooting out at speeds of up to 2,000 miles per hour. That's faster than a bullet. Jets can be powerful. They can push the comet around. They can change its rotation. They can even change its orbit slightly. Scientists call this the Yarkovsky effect. It's a small effect, but over millions of years, it can add up. It can change where a comet goes. Some scientists think that jets might be one reason why comets are so unpredictable. You never know when a new jet might start shooting out. Comets are also very old. Most of them formed about 4.6 billion years ago. That's when the solar system was born. They're made from the leftover material from the formation of the planets. They're like time capsules. They preserve the original material from the early solar system. This is why scientists study comets. By studying comets, we can learn about how the solar system formed. We can learn about what the early solar system was like. We can even learn about how life might have begun. Some scientists think that comets brought water and organic molecules to Earth. They think that comets might have helped life get started. But here's an interesting debate. Some researchers think comets brought most of Earth's water. Others think Earth already had water when it formed. The truth is probably somewhere in between. Comets likely brought some water, but maybe not all of it. The debate about Earth's water is fascinating. Scientists can tell where water came from by looking at what's called the deuterium ratio. Deuterium is a special kind of hydrogen atom. It's heavier than regular hydrogen. The ratio of deuterium to regular hydrogen in water tells scientists where that water formed. Water from comets has a different ratio than water from asteroids. Water from the early Earth would have yet another ratio. When scientists measured the deuterium ratio in Comet 67P's water, they found something surprising. It was much higher than Earth's ocean water. This suggests that comets like 67P probably didn't bring most of Earth's water. But other comets might have different ratios. Some comets might have ratios that match Earth's oceans better. The debate continues, with new measurements from each comet mission adding more pieces to the puzzle.
But here's what most scientists agree on. Earth probably got its water from multiple sources. Some came from comets, some came from asteroids. Some might have been here from the beginning. The exact mix is still being figured out. But one thing is clear. Comets contain a lot of water. A single comet could have billions of tons of water ice. If we could extract that water, it would be incredibly valuable for space exploration. Water can be used for drinking, for growing plants, and for making rocket fuel. Some researchers think that comets might be the gas stations of the future, providing water and fuel for missions to Mars and beyond. But extracting that water would be incredibly difficult, as we'll see when we think about building on a comet. Comets are also beautiful. When they're visible from Earth, they're amazing to see. They appear as bright objects in the sky, with long tails stretching behind them. Some comets are so bright that they can be seen during the day. Others are faint, visible only through telescopes. The most famous comet is probably Halley's Comet. It's been observed for thousands of years. Ancient records mention it. Chinese astronomers wrote about it in 240 BC. It appears in the Bayeux Tapestry, which shows the Norman conquest of England in 1066. It's been seen by people throughout history. It's a regular visitor to the inner solar system. The comet is named after Edmund Halley, who figured out in 1705 that the same comet kept coming back every 76 years. He predicted it would return in 1758, and he was right, though he didn't live to see it. But there are many other famous comets. Comet Hale-Bopp was visible for 18 months in 1996 and 1997. It was one of the brightest comets of the 20th century. It was so bright that people could see it even from cities with lots of light pollution. Comet Hyakutake was visible in 1996. It had a very long tail that stretched across half the sky. Comet Ison was discovered in 2012. Scientists thought it might become very bright, but it broke apart as it approached the sun. When it got too close, the sun's gravity and heat tore it apart into thousands of pieces. This shows how fragile comets can be. Even a large, bright comet can be destroyed in just a few days if it gets too close to the sun. Comets have also been visited by spacecraft. The first comet to be visited was Comet Halley in 1986. Several spacecraft flew past it, taking pictures and collecting data. Since then, other comets have been visited.
Comet Wild 2 was visited by the Stardust spacecraft, which collected samples of comet dust and brought them back to Earth. When scientists studied these samples, they found something surprising. The dust contained minerals that only form at very high temperatures near the Sun. This means some comet material might have formed close to the Sun, then been thrown out to the outer solar system. Comet 67P was visited by the Rosetta spacecraft, which actually landed on the comet's surface. The Philae lander touched down in 2014, though it bounced a few times before finally settling. It was the first time humans had ever landed on a comet. These missions have taught us a lot about comets. They've shown us what comets look like up close. They've revealed the structure of comet nuclei. They've shown us how comets behave. They've given us a much better understanding of these cosmic snowballs.
But there's still so much we don't know. We don't know exactly how comets form. We don't know why some comets are active and others are quiet. We don't know how long comets can survive. We don't know how many comets there are in the solar system. There are still many mysteries to solve. Some comets seem to die after a few trips around the Sun, losing all their ice and becoming just a dark rock. Others seem to last for millions of years. Scientists aren't sure why. Some researchers think it might depend on the comet's size, or how close it gets to the Sun, or what it's made of. But the truth is, we're still learning. Every new comet we study teaches us something new. And every answer seems to lead to more questions. That's what makes science so exciting. Comets are fascinating objects. They're ancient, they're mysterious, they're beautiful, they're important. They tell us about the history of the solar system. They might have brought water and life to Earth. They're cosmic travelers, drifting through space, carrying secrets from the beginning of time. And now, as we think about building a house on a comet, we need to understand what comets are really like. They're not just icy rocks. They're complex objects with active surfaces, changing as they approach the Sun. They're fragile, they're irregular, they're full of surprises. So, can you build a house on a comet? Well, that's a complicated question. It depends on what you mean by building a house. It depends on what kind of comet you're talking about. It depends on where the comet is in its orbit. There are many challenges, but there are also possibilities. Let's explore what it would really be like. Let's imagine what challenges you would face. Let's think about what solutions might work. Let's discover the science behind building a house on a comet. Chapter 2. The surface of a comet. What would you stand on? If you wanted to build a house on a comet, the first thing you'd need to do is land on it. But what would you land on? What is the surface of a comet actually like? This is a question that scientists have been trying to answer for decades. And thanks to spacecraft missions, we're starting to understand. The surface of a comet is not like the surface of Earth. It's not solid rock. It's not even solid ice. It's a mixture of ice and dust with lots of empty space in between. It's like a sponge, or like a pile of snow that's been partially melted and refrozen many times. When the Rosetta spacecraft visited Comet 67P, it discovered that the surface is incredibly varied. Some areas are smooth, some are rough, some are covered with boulders, some are covered with fine dust. Some areas are active, with jets of gas shooting out. Other areas are quiet, covered with a layer of dark material. The mission found that the surface temperature can change by more than 200 degrees Fahrenheit in just a few hours as the comet rotates.
Scientists were surprised to find that some areas of the comet are covered with a layer of fluffy dust that's only a few inches thick. This dust is so light that if you stepped on it, you might sink right through. The Philae lander gave us our first close-up look at a comet's surface. When it touched down, it used instruments to measure the surface properties. One instrument, called MUPUS, tried to hammer a probe into the surface, but it couldn't penetrate very far. The surface was much harder than expected. Scientists think the surface might have a layer of hard ice just beneath the dust. This hard layer might be several inches thick. Below that, the material gets softer again. It's like a comet sandwich with a hard layer in the middle. This structure is important for building. If you tried to anchor something to the surface, you'd need to get through the hard layer. But once you did, the material below might not be strong enough to hold an anchor. It's a real engineering challenge.
But here's what's really interesting. The Philae lander bounced when it tried to land. It bounced 3 times before finally settling. Scientists used these bounces to learn about the surface. By measuring how high the lander bounced and how long it took to come down, they could calculate the surface properties. They found that the surface is very soft in some places, like walking on a thick layer of powder. But in other places, it's hard, like walking on ice. The variety is amazing. You might step on soft dust in one spot, then take one step and be on hard ice. This makes it very hard to predict what the surface will be like in any given place. Even more surprising, scientists found that the surface isn't uniform at all. Some areas are covered with what they call goosebumps. These are small bumps about 10 feet across that cover large areas of the comet. Researchers believe these might be the original building blocks of the comet, preserved from when it first formed billions of years ago. Other areas have smooth, flat surfaces that look like they were carved by water, but there's no water flowing on comets. These smooth areas might be where dust has settled, or where ice has sublimated away evenly. The variety is amazing. In one area, you might see cliffs hundreds of feet tall. In another area, just a few feet away, you might see smooth, flat plains. It's like the comet has dozens of different landscapes, all mixed together. This makes it very hard to predict what the surface will be like in any given spot. You might think you found the perfect place to build, only to discover that the ground is actually just a thin layer of dust over empty space. The goosebumps are one of the most interesting discoveries from Rosetta. Scientists think these bumps might be the original pebbles that stuck together to form the comet. In the early solar system, tiny particles of ice and dust would have stuck together to form larger clumps. These clumps, maybe a few feet across, would have then stuck together to form the comet. The goosebumps might be these original clumps, still visible on the surface after billions of years. If this is true, it tells us that comets formed very gently, with particles just barely sticking together. There wasn't enough heat or pressure to melt everything together. The particles just kind of stuck, like cosmic Velcro. This gentle formation is why comets are so fragile. They were never really welded together. They're just held together by weak forces. But not all scientists agree about the goosebumps. Some researchers think they might have formed later, as the comet's surface changed. As ice sublimates, it might leave behind these bumps, or they might be formed by the way dust settles on the surface. The debate continues. But one thing is clear. The surface of a comet is incredibly complex, with features that formed over billions of years. Understanding these features is important if we ever want to build on a comet. We need to know what the surface is really like, not just what it looks like from far away. The surface is also very dark.
As we mentioned, comets reflect only 3 to 5% of the sunlight that hits them. That's darker than coal. The dark material is made of carbon-rich compounds, organic molecules. This material builds up on the surface as the comet ages. As ice sublimates, the dark stuff is left behind.
The dark coating is important. It affects how the comet heats up. Dark materials absorb more sunlight, so the dark coating helps the comet warm up. This makes the ice underneath sublimate faster. It creates a feedback loop. More sublimation means more dark material on the surface. More dark material means more heating. More heating means more sublimation. Scientists call this the runaway sublimation effect. Once it starts, it can accelerate quickly. On Comet 67P, researchers found that some areas became 10 times more active as the comet approached the Sun, all because of this feedback loop. The dark material is mostly made of complex organic compounds called tholins. These form when simple molecules are exposed to radiation. They're found on many icy worlds in the outer solar system, including Pluto and Saturn's moon Titan. But the surface is not uniform. Different areas have different properties. Some areas are covered with smooth, flat deposits. These might be places where dust has settled. Other areas are covered with rough, jagged terrain. These might be places where the surface has been eroded by jets. The surface also has cliffs. Some of them are hundreds of feet tall. These cliffs are made of ice and rock. They're held together by the weak gravity of the comet. But they're fragile. If you tried to climb one, it might collapse. The material is not strong enough to support much weight. On Comet 67P, there's a cliff called Hathor that's about 3,000 feet tall. That's taller than the Empire State Building. But because the gravity is so weak, if a piece of rock fell off this cliff, it would take about 20 minutes to hit the ground. On Earth, the same fall would take just a few seconds. The low gravity makes everything happen in slow motion. Scientists actually watched this happen. The Rosetta spacecraft saw boulders falling from cliffs on Comet 67P. But because the gravity is so weak, the boulders didn't fall straight down. They kind of drifted, floating slowly through space. Some boulders even escaped the comet entirely, floating away into space forever. This is a real problem for building. If you tried to build near a cliff, rocks could fall on your house. But because of the weak gravity, they'd fall so slowly that you might not even notice until it was too late. And if a boulder escaped the comet's gravity, it could float away and hit your house from any direction. You'd need to be very careful about where you build. Some researchers think you might need to build in areas that are completely flat, away from any cliffs or steep slopes. But even then, you'd still have the problem of the surface itself being unstable. Rosetta watched the comet's surface change in real time. Over the 2 years it spent orbiting the comet, scientists saw dramatic changes. Cliffs collapsed. New pits appeared. Boulders moved. The surface was constantly changing. One cliff, called Aswan, collapsed completely. Scientists watched it happen. First, cracks appeared. Then, over several weeks, the cliff slowly crumbled. Finally, it collapsed in a huge landslide. But because the gravity is so weak, the landslide happened in slow motion. Rocks drifted down like they were falling through water, not air. Some rocks escaped the comet entirely, becoming tiny moons that orbited around it. Others fell back down, but so slowly that it took hours or even days. If you were building near that cliff, you'd have plenty of warning.
But you'd also have to watch rocks drift around for days, not knowing where they'd land.
Scientists use these observations to understand how comets change. They found that most changes happen when the comet is close to the sun. As the ice heats up and sublimates, it weakens the surface. Cracks form. Material becomes unstable. Then, when something triggers it, like a small impact or just the comet's rotation, the surface collapses. But the changes aren't random. Scientists can predict which areas are most likely to change. Steep slopes are more dangerous. Areas with lots of cracks are unstable. Areas that face the sun are more active. By studying these patterns, scientists hope to understand where it might be safe to build. But the truth is, nowhere on a comet is completely safe. The surface is always changing, always active. Building on a comet would be like building on a mountain that's constantly reshaping itself. The surface also has pits. These are holes in the surface, sometimes hundreds of feet deep. They might be caused by jets. As gas escapes from the interior, it might create these pits. Or they might be caused by the comet breaking apart. As the comet rotates and heats up, different parts expand and contract. This can create cracks and pits. Scientists found that some pits on Comet 67P are more than 600 feet deep. That's deeper than the Washington Monument is tall. These pits might be sinkholes where the surface has collapsed into empty spaces underneath. Some researchers think the comet might be hollow in places, like a cosmic Swiss cheese. This would make building even more dangerous because you never know when the ground might collapse beneath you. The surface also has boulders, big rocks scattered across the surface. Some of them are the size of houses. Some are even bigger. On Comet 67P, scientists found boulders that were more than 150 feet across. That's bigger than a 10-story building. These boulders are probably pieces of the comet that broke off and fell back down. Or they might be material that was never part of the original comet but got stuck to the surface somehow. Some scientists think these boulders might have formed when the comet was first created, billions of years ago. The boulders are interesting because they tell us about the comet's history. They show us that the comet has been active. It has been changing. Pieces have broken off. Material has moved around. The surface is not static, it's dynamic. The surface also has layers, like an onion. Different layers have different properties. The outer layer is dark and dusty. It's the material that's been left behind as ice sublimates. Underneath, there's ice, but the ice is not pure. It's mixed with dust and rock, and it's full of holes. The layers tell us about the comet's history. They show us how the comet has changed over time. As the comet approaches the sun, the outer layers heat up first. The ice sublimates. The dark material is left behind. This creates the dark coating. But as the comet moves away from the sun, the process slows down. New layers might form. Scientists studying Comet 67P found that the layers can be very thin, sometimes only a few inches thick, but they can also be hundreds of feet thick in some places. The layers are like tree rings, recording the comet's history. Each time the comet passes close to the sun, it loses a layer. Some researchers estimate that Comet 67P has lost about 10% of its mass since it started coming close to the sun. That means it might only survive for a few thousand more orbits before it completely disappears. The surface is also very cold. When the comet is far from the sun, the surface temperature can be minus 400 degrees Fahrenheit. That's incredibly cold.
cold enough to freeze almost anything. But as the comet approaches the Sun, the temperature rises. Near the Sun, the surface can reach 100 degrees Fahrenheit or more. That's a huge temperature swing. When Rosetta measured Comet 67P's temperature, it found that the surface could heat up to 122 degrees Fahrenheit when facing the Sun. But just a few feet away, in the shadow, it stayed at minus 238 degrees. This extreme difference happens because there's no atmosphere to spread the heat around. Scientists discovered something even more extreme. They found that the temperature can change by hundreds of degrees in just minutes as the comet rotates. One area might be in sunlight, heating up to over 100 degrees. Then, as the comet rotates, that same area moves into shadow and cools down to minus 200 degrees in just a few minutes. This rapid temperature change is a huge problem for building materials. Most materials on Earth expand when they heat up and contract when they cool down. But if the temperature changes hundreds of degrees in minutes, the expansion and contraction happens so fast that materials can't keep up. They crack, they break, they shatter. Engineers have studied this problem. They found that even materials designed for space, like titanium and special alloys, would have trouble with these rapid temperature changes. Some researchers think you might need to use materials that don't expand or contract much, like certain types of ceramics or composites. But these materials are often brittle and can break easily. It's a real engineering challenge. This temperature change is a problem for building a house. Materials expand and contract as they heat up and cool down. If you built a house on a comet, it would have to survive these extreme temperature changes. Most materials can't handle that. They would crack, they would break, they would fail. Engineers have studied this problem. They found that most metals expand by about 0.01% for every 100 degrees of temperature change. Over a 500-degree temperature swing, that's a 0.05% expansion. For a 100-foot-long structure, that's about half an inch of expansion. But the real problem is that different materials expand at different rates. If you used steel and aluminum together, they would expand at different rates and pull apart. You'd need to use materials with similar expansion rates, or design joints that can handle the movement. So researchers think you might need to use flexible materials, like certain plastics or composites, that can handle large temperature changes without breaking. The surface is also very low gravity. A typical comet has a gravity that's about 1/10,000th of Earth's gravity. That means if you weighed 100 pounds on Earth, you would weigh only 0.01 pounds on a comet. You would be almost weightless. On Comet 67P, the escape velocity is only about 1 mile per hour. That means if you jumped at just 1 mile per hour, you would float away into space forever. Compare that to Earth, where you need to go more than 25,000 miles per hour to escape. This is why the Rosetta lander had to use harpoons and screws to anchor itself to the comet's surface.
But here's what actually happened with the Philae lander. It tried to anchor itself using harpoons, but the harpoons didn't fire properly. The lander bounced. It bounced 3 times before finally coming to rest. The first bounce took it about 3,000 feet into the air. The second bounce was smaller, only about 100 feet. The third bounce was tiny, just a few inches. Then it finally settled. But because the harpoons didn't work, the lander wasn't properly anchored. It ended up in a shadowy area where its solar panels couldn't get enough sunlight. It only worked for a few days before its batteries ran out. This shows how hard it is to land on a comet. Even with careful planning and advanced technology, things can go wrong.
The weak gravity makes everything unpredictable. If you tried to build a house, you'd face the same problems. How do you anchor something when the surface is so weak? How do you keep it from bouncing or floating away? It's a real challenge that scientists are still trying to solve. This low gravity is a problem for building. On Earth, gravity holds things down. It keeps buildings stable. It keeps materials in place. But on a comet, there's almost no gravity. Things would float away. A house would need to be anchored somehow. But how do you anchor something to a surface that's mostly ice and dust? The surface is also unstable. It's constantly changing. As the comet approaches the sun, ice sublimates, gas escapes, the surface erodes, material moves around, boulders fall, cliffs collapse. The surface is not a stable place to build. When Rosetta watched Comet 67P, it saw the surface changing in real time. A cliff collapsed, sending boulders tumbling. A new pit appeared where there wasn't one before. The comet was losing about 1,000 pounds of material every second as it approached the sun. That's like losing the weight of a small car every second. Over the course of its orbit, the comet could lose millions of tons of material. Your house might be sitting on ground that's literally disappearing beneath you. The surface is also full of hazards. Jets can shoot out gas and dust at high speeds. These jets can be dangerous. If you were standing near one, you could be hit by high-speed particles. The jets can also change the comet's rotation, which could throw you off balance. Scientists have measured the force of these jets. On Comet 67P, some jets were strong enough to lift a person off the surface, even with the comet's weak gravity. The particles in the jets can travel at speeds of up to 1,000 miles per hour. If one of these particles hit you, it would be like being hit by a bullet. The jets also create a kind of wind on the comet's surface, even though there's no atmosphere. This wind can move dust and small rocks around. Some researchers think you might need to build your house in a quiet zone, away from active jet areas. But the problem is that jets can appear anywhere, at any time, as the comet heats up. The surface is also exposed to space. There's no atmosphere, no protection from radiation, no protection from meteoroids. If you were on the surface, you would be exposed to all the dangers of space. You would need a spacesuit just to survive. Interestingly, even though there's no atmosphere, the comet itself creates a kind of temporary atmosphere when it's active. The gas streaming off the comet creates a very thin atmosphere around it. This atmosphere is so thin that it would be considered a vacuum on Earth, but it's still there. This thin atmosphere can actually protect you from some radiation, but not much. It's like having a sheet of paper between you and a nuclear reactor. It helps a tiny bit, but you'd still need much more protection. The comet's atmosphere also means that small meteoroids might burn up before hitting the surface, but larger ones would still get through. You'd need to be prepared for impacts. But despite all these challenges, the surface does have some advantages. It's made of ice, which means there's water. If you could extract the water, you could use it for drinking, for growing plants, for making rocket fuel. Water is one of the most valuable resources in space. The surface also has organic molecules, carbon-based compounds. These could be used to make materials. They could be used to grow food. They could be used for many things. Organic molecules are the building blocks of life. Having them available could be very useful. The surface is also relatively clean. There's no pollution, no contamination from Earth. It's a pristine environment. This could be useful for scientific research or for manufacturing things that need a clean environment. But the biggest challenge is the low gravity. How do you build a house when there's almost no gravity? How do you keep materials in place? How do you keep the house from floating away? One solution might be to use anchors. You could drill into the surface and anchor the house to the comet. But the surface is fragile. It might not be strong enough to hold anchors. And as the surface erodes, the anchors might come loose. Another solution might be to use the comet's rotation. If you built the house in the right place, the rotation might create a small amount of artificial gravity. But it would be very small, and it would only work if you were far enough from the center of rotation. Another solution might be to build the house inside the comet. You could dig a hole or find a cave. Then you could build the house inside, protected from the surface hazards. But digging into a comet would be difficult. The material is fragile. It might collapse. And you would still have the problem of low gravity. Another solution might be to use a different approach entirely. Instead of building a traditional house, you could use an inflatable structure. Or you could use a structure that's designed to work in low gravity. But this would require new materials and new construction techniques. The surface of a comet is a challenging place. It's dark, it's cold, it's unstable. It has almost no gravity. It's constantly changing. But it's also interesting. It has water, it has organic molecules. It's a pristine environment. It's a place where new things might be possible. Building a house on a comet would be difficult, but it might not be impossible. It would require new technologies, new materials, new approaches. But humans are good at solving problems. We've built things in space before. We've built things on the moon. We've built things on Mars. Maybe we could build something on a comet too. But first, we need to understand the surface better. We need to know what it's really like. We need to know what challenges we would face. And we need to know what solutions might work. The surface of a comet is a mystery. It's a place we're still learning about. Every mission teaches us something new. Every discovery reveals new challenges and new possibilities. As we think about building a house on a comet, we need to remember that the surface is not like Earth. It's not like the Moon. It's not like Mars. It's unique. It's a place unlike any other. And that's what makes it interesting. That's what makes it worth exploring. Chapter 3: The Challenges of Living on a Comet. Gravity, temperature, and more. Living on a comet would be unlike living anywhere else. It would present challenges that we've never faced before. Some of these challenges are obvious, others are more subtle. But all of them would need to be solved if we wanted to build a house and live on a comet. The biggest challenge is probably gravity, or rather, the lack of it. A typical comet has a gravity that's about 1/10,000th of Earth's gravity. That's incredibly weak. If you jumped, you might never come back down. You could float away into space with just a small push.
This low gravity affects everything. It affects how you move. It affects how you build. It affects how you live. On Earth, gravity is always pulling you down. It keeps your feet on the ground. It keeps things in place. But on a comet, there's almost no gravity. Everything floats. If you tried to walk on a comet, you would have to be very careful. A normal step might launch you into the air. You might float away. You would need to move slowly. You would need to hold on to something. Or you would need to use some kind of propulsion system to keep yourself anchored.
building would be even more difficult. On Earth, you can stack bricks, you can pour concrete, you can build walls that stand up. But on a comet, nothing stays in place. Bricks would float away, concrete wouldn't work, walls wouldn't stand up. You would need a completely different approach. You might need to use anchors. You could drill into the comet and anchor your structure. But the comet's surface is fragile. It might not be strong enough to hold anchors. And as the comet rotates and heats up, the surface changes. Anchors might come loose. You might need to use tension. You could build a structure that's held together by cables under tension, like a tent. The cables would pull the structure together, keeping it stable. But this would require a strong anchor point, and you would still have the problem of the fragile surface. You might need to use rotation. If you built your structure far enough from the comet's center of rotation, the rotation might create a small amount of artificial gravity. But it would be very small, and it would only work in certain places. You might need to use a different approach entirely. Instead of building on the surface, you could build inside the comet. You could dig a tunnel or find a cave. Then you could build your house inside, where you would be protected from the surface hazards. But digging into a comet would be difficult. The material is fragile. It might collapse. Another challenge is temperature. Comets experience extreme temperature changes. When a comet is far from the sun, the temperature can be -400 degrees Fahrenheit. That's incredibly cold, cold enough to freeze almost anything. But as the comet approaches the sun, the temperature rises. Near the sun, the surface can reach 100 degrees Fahrenheit or more. That's a temperature swing of 500 degrees. This temperature change is a problem for materials. Most materials expand when they heat up and contract when they cool down. If you built a house on a comet, it would have to survive these extreme temperature changes. Most materials can't handle that. They would crack, they would break, they would fail. You would need materials that can handle extreme temperatures. You might need special alloys, or you might need to use insulation to protect your structure from temperature changes. But insulation adds weight and complexity. Some researchers have studied materials that might work. One option is titanium, which can handle temperatures from -400 to over 1,000 degrees Fahrenheit. But titanium is expensive and hard to work with. Another option is certain ceramics, which can handle even wider temperature ranges. But ceramics are brittle and can crack. Some scientists think you might need to use a combination of materials with insulation between layers. The insulation would need to be very effective. On Earth, good insulation might be a few inches thick. On a comet, you might need insulation that's several feet thick to handle the extreme temperature swings. That's a lot of material, and it all has to be brought from Earth or made on the comet. Engineers have been studying this problem for years. NASA and other space agencies have tested materials in extreme conditions. They found that most materials expand and contract as temperatures change. This expansion and contraction can cause problems. If two materials are connected and they expand at different rates, they can pull apart, or they can create stress that causes cracks. On a comet, with temperature swings of 500 degrees or more, this is a huge problem. A structure that works perfectly when the comet is cold might break apart when it gets hot, or vice versa. Some researchers think the solution might be to use materials that don't expand much. There are special alloys that have very low expansion rates. But these materials are expensive and hard to work with. Other researchers think you might need to design structures that can move and flex as temperatures change, like a building that can breathe as it heats up and cools down. But this adds complexity.
And on a comet, complexity is dangerous. The more complex something is, the more ways it can break. Some engineers think the best solution might be to bury the structure deep underground, where temperatures are more stable. But as we've seen, digging into a comet is incredibly difficult. The material is fragile and might collapse. It's a problem with no easy solution. The temperature change also affects the comet itself. As the comet heats up, ice sublimates, gas escapes, the surface erodes, material moves around, the comet changes shape. Your house might be on stable ground one day and floating in space the next. Another challenge is the lack of atmosphere. Comets have no atmosphere, no air to breathe, no protection from radiation, no protection from meteoroids. If you were on a comet, you would be exposed to all the dangers of space. You would need a spacesuit just to go outside, or you would need to live in a sealed environment. Your house would need to be airtight. It would need life support systems. It would need air, water, and food. It would need to remove waste. It would need to maintain the right temperature and pressure. Life support systems are complex. On the International Space Station, they recycle about 93% of the water. They also recycle some of the air, removing carbon dioxide and adding oxygen. But these systems require a lot of energy and maintenance. On a comet, you'd need to be even more efficient. Some researchers think you might need to recycle 99% or more of your water. You'd also need to extract oxygen from water, which requires electricity. A typical person needs about 0.84 kilograms of oxygen per day. To produce that from water, you'd need to split about 0.95 kilograms of water, which requires about 4 kilowatt-hours of electricity. That's a lot of power, especially when solar panels aren't working well. This is similar to living on a space station. But on a space station, you can resupply from Earth. On a comet, you would be far away. Resupply would be difficult and expensive. You would need to be more self-sufficient. Another challenge is radiation. In space, there's no atmosphere to protect you from radiation. You would be exposed to cosmic rays, solar radiation, all kinds of dangerous particles. This radiation can cause cancer. It can damage electronics. It can be deadly. Astronauts on the International Space Station receive about 10 times more radiation than people on Earth. On a comet, far from Earth's magnetic field, you'd get even more. Some scientists estimate you might receive 50 to 100 times more radiation than on Earth. You would need protection from radiation. Your house would need thick walls, or you would need to build underground, or you would need some other form of shielding. But radiation protection adds weight and complexity. Some researchers think you might need walls that are at least 3 feet thick to protect against cosmic radiation. That's a lot of material to bring from Earth or extract from the comet. Scientists discovered something that might help. They found that water is actually a good radiation shield. A few feet of water can block most cosmic radiation. And comets have lots of water ice. So you could potentially use the comet's own ice as radiation protection. You could build your house and then cover it with ice. Or you could build inside a cave and line the walls with ice. But there's a problem. When the comet gets close to the sun, the ice would start to sublimate. Your radiation shield would literally evaporate. You'd need to constantly add new ice or find a way to keep it frozen even when the comet is hot. Some researchers think you might need to use a combination of materials. Ice for when the comet is cold and other materials for when it's hot. But this adds complexity and cost. It's another challenge that would need to be solved. Radiation is a serious problem in space. Astronauts on the International Space Station are protected by Earth's magnetic field, which deflects most cosmic radiation. But on a comet, far from Earth, there's no such protection. You'd be exposed to cosmic rays, solar radiation, and all kinds of dangerous particles. Scientists have measured radiation levels in space, and they're much higher than on Earth. An astronaut on a comet might receive 50 to 100 times more radiation than someone on Earth. Over time, this radiation can cause cancer, damage DNA, and harm the nervous system. It's not something you can ignore. But here's an interesting idea. Some researchers think you might be able to use the comet's own material as a radiation shield. If you buried your house deep enough, the comet's material above you would block most radiation. Scientists have calculated that you'd need about 10 feet of comet material to provide good protection. But there's a problem. As we've seen, the comet's material is mostly empty space, so you'd need even more material to get the same protection, maybe 30 or 40 feet. That's a lot of digging. And you'd still have the problem of the material sublimating away when the comet gets hot. It's a challenging problem, but not impossible. Some researchers think it might be worth the effort. After all, radiation protection is critical for long-term survival. Another challenge is the comet's activity. As a comet approaches the sun, it becomes active. Ice sublimates, gas escapes, jets shoot out, the surface changes. This activity could be dangerous. Jets could hit your house. The surface could collapse. Material could fall on you. You would need to predict when the comet would be active. You would need to protect your house from jets. You would need to anchor it securely. But predicting comet activity is difficult. Comets are unpredictable. They can surprise you. Scientists have been trying to predict comet activity for decades, but it's still not very accurate. They can predict when a comet will be close to the sun, which is when it's most likely to be active, but they can't predict exactly when jets will appear or how strong they'll be. Some comets become active when they're still far from the sun. Others stay quiet until they're very close. Comet 67P surprised scientists by becoming active when it was still 3 times farther from the sun than Earth. No one expected that. This unpredictability makes it hard to plan. You might build your house in what seems like a safe area, only to have jets start shooting out nearby. Some researchers think you might need to build your house on a platform that can move, so you can relocate if jets appear too close. Another challenge is the comet's rotation. Comets rotate, but their rotation is often irregular. They might wobble, they might tumble. This makes it hard to predict where the sun will be. It makes it hard to plan. It makes it hard to build. If you built a house on a rotating comet, you would experience day and night. But the length of day and night would change as the comet rotated. And if the rotation was irregular, the pattern would be unpredictable. You might have a 10-hour day, followed by a 5-hour day, followed by a 20-hour day. This would make it hard to maintain a schedule. Scientists have found that some comets have very irregular rotation. Comet 67P's rotation period changed by about 20 minutes over the course of its orbit. That might not sound like much, but it means that a day on the comet could be anywhere from 12.2 to 12.6 hours long, depending on where the comet is in its orbit. This irregularity is caused by the jets. As jets shoot out, they act like tiny rocket engines, speeding up or slowing down the comet's rotation. Some researchers think that over millions of years, a comet's rotation could change dramatically. A comet that starts with a 12-hour day might end up with a 6-hour day or even start rotating backwards. This would make it impossible to have a regular schedule. You'd need to adapt to whatever the comet's rotation happened to be at that moment. Another challenge is the comet's orbit. Comets have elliptical orbits. They get close to the sun, then move far away. This means the environment changes dramatically. When the comet is close to the sun, it's hot and active. When it's far from the sun, it's cold and quiet. If you lived on a comet, you would experience these changes. You would need to adapt. You would need different systems for different parts of the orbit. You would need heating when the comet is far from the sun. You would need cooling when it's close to the sun. You would need to protect yourself from activity when the comet is active. Another challenge is resources. Comets have water, they have organic molecules, but extracting these resources would be difficult. You would need equipment. You would need energy. You would need to process the materials. This would require a lot of infrastructure. Scientists have studied how to extract water from comets. One method is to heat the comet's surface, causing the ice to sublimate. Then you'd collect the water vapor and condense it back into liquid. But this requires a lot of energy. To extract just 1 gallon of water, you might need to heat several tons of comet material. Another method is to dig into the comet and extract ice directly. But as we've seen, the comet's material is fragile and might collapse. Some researchers think you might need to use a combination of methods. You could use solar power when the comet is close to the sun to heat the surface and extract water. Then you'd store the water for use when the comet is far from the sun. But storing large amounts of water in space is difficult. It would need to be kept from freezing or boiling, depending on the temperature. You'd need insulated tanks and heating or cooling systems, which all require energy. You would also need energy to power your house, to extract resources, to maintain life support. You might need nuclear power, or you might need to store energy for the long journey away from the sun. Some scientists think a small nuclear reactor might be the only practical solution for long-term power on a comet.
But here's a problem with nuclear power. Nuclear reactors need to be cooled. On Earth, we use water or air to cool reactors. But on a comet, there's no atmosphere, and water is valuable. You'd need to bring cooling systems from Earth, which adds weight and cost. Some researchers think you might be able to use the comet's ice as a coolant. You could melt ice to cool the reactor, then use the heat to extract more water. It's like a cycle. But this would require a lot of engineering. And there's another problem. Nuclear reactors produce waste. On Earth, we can store nuclear waste safely. But on a comet, where would you put it? You couldn't just dump it on the surface. It would contaminate the comet. You'd need to bring it back to Earth or find some other way to handle it. This is why some scientists think solar power might still be the best option, even when the comet is far from the sun. You'd just need huge solar panels, and you'd need to store a lot of energy for when the comet is far away. It's a difficult problem with no easy solution. Another challenge is communication. Comets are far away. Communicating with Earth would be difficult. There would be delays. The signal would be weak. You would feel isolated. You would need reliable communication systems. But even with the best systems, you would be far from home. When the Rosetta spacecraft was at Comet 67P, it took radio signals about 30 minutes from the comet to Earth. That means if you sent a message, you'd wait an hour to get a reply. At the comet's farthest point from Earth, the delay could be hours, and the signal would be incredibly weak. You'd need huge antennas, both on the comet and on Earth, just to send simple messages.
It would be like trying to have a conversation by whispering across an ocean. Another challenge is psychology. Living on a comet would be lonely. You would be far from Earth. You would be in a small space. You would be surrounded by darkness. This could be hard on your mental health. You'd need ways to stay connected. You would need ways to stay busy. You'd need ways to stay sane. Scientists who study isolation have found that people in extreme isolation can develop serious mental health problems. Astronauts on the International Space Station have support from mission control and can see Earth. But on a comet, you'd be truly alone. Some researchers think that living on a comet might be harder psychologically than living on Mars, because at least on Mars, you could see Earth in the sky. On a comet far from the Sun, Earth might be invisible, just a tiny dot lost among the stars. You'd need to be incredibly mentally strong to handle that kind of isolation. Scientists have studied people who live in extreme isolation on Earth, and the findings are interesting. Like researchers in Antarctica during the winter, when it's dark for months. They found that people can adapt, but it's not easy. Some people develop depression. Some have trouble sleeping. Some become irritable or anxious. But others do fine. They find ways to stay busy. They create routines. They stay connected with others, even if it's just through delayed messages. The key seems to be having a sense of purpose and meaningful work. On a comet, your work would be critical for survival. That might actually help. You'd be too busy trying to stay alive to get depressed. But you'd also be under constant stress, which could make things worse. It's a complicated problem. Some researchers think that living on a comet might require psychological screening and training, similar to what astronauts go through, but even more intense. You'd need to be someone who can handle extreme isolation, uncertainty, and stress. Not everyone could do it, and even people who think they can handle it might discover they can't once they're actually there. It's a risk that would need to be carefully considered.
Psychologists have been studying isolation for decades. They've looked at people in submarines, in space stations, in remote research stations. They found that isolation affects different people in different ways. Some people thrive in isolation. They enjoy the quiet, the focus, the lack of distractions. Others struggle. They need social interaction, variety, connection. The key is knowing which type you are. But even people who think they can handle isolation might discover they can't once they're actually isolated. It's hard to predict how someone will react. On a comet, the isolation would be extreme. You'd be millions of miles from Earth. Communication would be delayed by hours. You couldn't just call for help if something went wrong. You'd be truly alone. Some researchers think this might actually be easier than being in a small group. When you're alone, you don't have to deal with other people's problems. You can focus on your work. But when you're in a group, you have to deal with conflicts, personality clashes, and the stress of living in close quarters. Both situations are challenging, but in different ways. The best approach might be to have a small, carefully selected crew. People who are compatible, who can work together, who can handle the stress. But even then, things can go wrong. People can change. Relationships can break down. It's a risk that can't be eliminated, only managed. But despite all these challenges, there are also opportunities. Comets have water. Water is valuable in space. You could use it for drinking, for growing plants, for making rocket fuel. If you could extract water from a comet, you could create a refueling station.
you could support missions to other parts of the solar system. Comets also have organic molecules. These could be used to make materials. They could be used to grow food. They could be used for many things. Having these resources available could be very useful. Comets are also interesting scientifically. They preserve material from the early solar system. By studying comets, we can learn about how the solar system formed. We can learn about what the early solar system was like. Having a research station on a comet could be very valuable. Comets are also relatively easy to reach. Compared to other objects in the outer solar system, comets are closer. Some comets come close to Earth. This makes them more accessible. It makes them easier to visit. It makes them easier to build on. But here's the catch. While some comets come close to Earth, they're moving very fast when they do. Comet 67P was traveling at about 84,000 miles per hour when Rosetta caught up to it. That's 10 times faster than a bullet. To land on a comet, you'd need to match its speed, which requires a lot of fuel. The Rosetta mission took 10 years to reach Comet 67P, using gravity assists from Earth and Mars to save fuel. A direct mission would take even longer and require even more fuel. Some researchers think that the best approach might be to wait for a comet that's already in a stable orbit close to Earth, or to use a comet that's been captured into orbit around Earth or the Moon. But capturing a comet would be incredibly difficult and would require technology we don't have yet. So while comets might be easier to reach than other outer solar system objects, they're still incredibly difficult to reach and land on. But the challenges are real. They're significant. They would require new technologies, new materials, new approaches. But humans are good at solving problems. We've overcome challenges before. We've built things in space. We've lived in space. Maybe we could live on a comet too. The key is to understand the challenges, to plan for them, to develop solutions, to test them, to be prepared. Living on a comet would be difficult, but it might not be impossible. It would be an adventure. It would be a challenge. It would be something new. And that's what makes it interesting. That's what makes it worth exploring. The challenges are real, but so are the possibilities. The future is unknown, but it's also full of potential. Chapter 4: Building Materials and Construction. What would you use? If you wanted to build a house on a comet, you would need to think carefully about what materials to use. The materials that work on Earth won't necessarily work on a comet. The environment is too different. The challenges are too unique. You would need new materials, new approaches, new ideas. Let's think about what materials might work. First, let's consider the comet itself. Comets are made of ice and rock. Could you use these materials to build? Well, maybe. Ice could be used as a building material. You could melt it and refreeze it into shapes. You could build structures out of ice. But ice has problems. It's fragile. It melts when it gets warm. It's not very strong. You would need to reinforce it. You might need to mix it with other materials. Or you might need to keep it very cold. But if you're building on a comet, keeping things cold might not be a problem when the comet is far from the sun. Some researchers have studied building with ice in space. They found that ice mixed with fiberglass or other materials can be surprisingly strong. But there's a problem. When the comet gets close to the sun, even reinforced ice would start to sublimate. Your ice house would literally evaporate. you'd need to constantly add new ice or find a way to keep it frozen even when the comet is hot. Some scientists think you might need to bury your ice structure deep underground, where it would stay cold even when the surface heats up. Ice also has some advantages. It's available. You don't need to bring it from Earth. You can extract it from the comet. It's also a good insulator. It can protect you from temperature changes, and it can provide radiation shielding. But using ice as a building material would require new techniques. You would need to figure out how to shape it, how to join pieces together, how to make it strong enough. This would be a challenge, but it might be possible. Rock is another option. Comets have rock. You could use it to build. But comet rock is different from Earth rock. It's mixed with ice. It's porous. It's fragile. It might not be strong enough for construction. When scientists studied samples from Comet Wild 2, they found that the rock was mostly made of silicates, similar to Earth rocks. But the structure was very different. The rock was full of tiny holes and gaps, making it very light and weak. Some pieces were so fragile that they crumbled when touched. The rock also contained materials that don't exist on Earth, like certain types of glass that formed in space. Some researchers think you might be able to process this rock to make it stronger. You could heat it to remove the ice, then compress it to close the holes. But this would require a lot of energy and equipment. And even then, the processed rock might not be as strong as Earth rock. It might work for some purposes, but probably not for major structural elements. You could also bring materials from Earth, but that would be expensive. Every pound you bring from Earth costs thousands of dollars, and you would need a lot of material to build a house. This would be very expensive. Right now, it costs about $10,000 to send 1 pound of material into space. To send it to a comet would cost even more, maybe $50,000 or $100,000 per pound. A typical house on Earth weighs about 200,000 pounds. To send that much material to a comet would cost billions of dollars. That's why scientists are so interested in using local materials. If you can build with comet ice and rock, you'd only need to bring tools and equipment from Earth, not the building materials themselves. This could reduce the cost by 90% or more.
You might be able to use 3D printing. You could bring a 3D printer and print structures using local materials. You could use comet ice and dust as printing material. This would reduce the amount of material you need to bring from Earth. NASA has already tested 3D printers on the International Space Station. They've printed tools and parts using plastic. But printing with comet ice and dust would be much harder. The material would need to be melted and shaped, which requires a lot of energy. And the printed structures would need to be strong enough to handle extreme temperatures and low gravity. 3D printing in space is still experimental, but it's showing promise. On the International Space Station, astronauts have printed tools, parts, and even medical devices. The printer works in zero gravity, which is important, but printing with comet materials would be much more challenging. You'd need to melt the ice, mix it with dust, and then shape it into structures. But there's a problem. Ice sublimates in vacuum. It doesn't melt, it turns directly into gas. So you'd need to work in a pressurized environment or find a way to keep the ice from sublimating. Some researchers think you might be able to use a process called sintering, where you heat the material just enough to make it stick together, but not enough to melt it. This has been tested on Earth, but never in space. It's an interesting idea, but it would require a lot of research and development. Another challenge with 3D printing is that the printed structures need to be strong.
On Earth, 3D printed objects can be weak because the layers don't always stick together perfectly. In space, with low gravity and extreme temperatures, this could be even worse. The printed structure might crack or break apart. Some researchers think you might need to reinforce the printed material with fibers or other materials. But that adds complexity. And on a comet, complexity is dangerous. The more complex something is, the more ways it can fail. But 3D printing in space is still experimental. It's not proven. It would require new technologies, new materials, new techniques. But it's an interesting possibility. Some researchers think that 3D printing might be the key to building on other worlds. If we can figure out how to do it with local materials, we wouldn't need to bring everything from Earth. You could also use inflatable structures, like a balloon. You could bring a deflated structure from Earth, then inflate it on the comet. This would be lighter and smaller during transport. And inflatable structures can be strong. They're used on the International Space Station. NASA has been testing inflatable habitats for years. The Bigelow Expandable Activity Module, or BEAM, was tested on the space station and worked well. It's made of layers of fabric that are stronger than steel when inflated. But on a comet, you'd need to protect it from jets and temperature changes that could damage the material. Inflatable structures have some big advantages. They're lightweight, which means they're cheaper to launch. They can be packed into a small space, then expanded once they reach the comet. And they can be surprisingly strong. The beam module on the space station has been working for years, and it's held up well. But there are challenges. The material needs to be airtight, which means it can't have any leaks. Even a tiny leak could be a problem in space. The material also needs to be strong enough to resist punctures from micrometeorites or debris, and it needs to handle extreme temperatures without cracking or becoming brittle.
On a comet, there are additional challenges. Jets of gas and dust could hit the structure, potentially causing damage. The extreme temperature changes could cause the material to expand and contract, creating stress. And the low gravity means the structure would need to be anchored securely, or it might float away. Some researchers think you might need to cover the inflatable structure with a layer of comet material for protection, but that adds weight and complexity. It's a trade-off. Inflatable structures are lighter and easier to transport, but they might need more protection once they're deployed. But inflatable structures have problems. They need to be airtight. They need to be strong enough to hold pressure. They need to be protected from punctures, and they need to be anchored somehow. But they might work. You could also use a combination of approaches. You could use an inflatable structure as the main living space. Then you could build additional structures using local materials. Or you could use a hybrid approach, combining different materials and techniques. But whatever materials you use, you would need to anchor your structure. The low gravity means that nothing stays in place. You would need to secure your house to the comet somehow. One approach is to use anchors. You could drill into the comet and insert anchors. Then you could attach your structure to the anchors. But the comet's surface is fragile. It might not be strong enough to hold anchors. And as the surface erodes, the anchors might come loose. Another approach is to use the comet's rotation. If you built your structure far enough from the comet's center of rotation, the rotation might create a small amount of artificial gravity. This could help keep things in place. But it would be very small, and it would only work in certain places. Another approach is to build inside the comet. You could dig a tunnel or find a cave. Then you could build your house inside, where you would be protected from the surface hazards.
But digging into a comet would be difficult. The material is fragile. It might collapse. Another approach is to use a different design entirely. Instead of a traditional house, you could use a structure that's designed to work in low gravity, like a space station or like a submarine, something that's self-contained and doesn't need to be anchored. But whatever approach you use, you would need to think about the environment, the temperature changes, the lack of atmosphere, the radiation, the activity. All of these would affect your structure. You would need insulation to protect against temperature changes. You would need airtight seals to maintain atmosphere. You would need radiation shielding. You would need protection from jets and other hazards. You would also need life support systems, air, water, food, waste removal, temperature control, pressure control. All of these systems would need to be integrated into your structure. Life support systems are incredibly complex. On the International Space Station, the life support system takes up about 20% of the station's volume and uses about 30% of its power. And that's with regular resupply from Earth. On a comet, you'd need to be completely self-sufficient. The system would need to recycle almost everything. Water from breathing, sweating, and waste would need to be purified and reused. Carbon dioxide from breathing would need to be removed and converted back into oxygen. Waste would need to be processed, with useful materials extracted and reused. All of this requires energy, and all of it can fail. If your life support system breaks down, you'd have only hours or days to fix it before you'd run out of air or water. That's why redundancy is so important. You'd need backup systems for your backup systems. Some researchers think you might need 3 or 4 independent life support systems just to be safe.
Life support systems are one of the most critical parts of any space habitat. On the International Space Station, the system recycles about 93% of the water. That's pretty good, but on a comet, you'd need to do even better. Some researchers think you'd need to recycle 99% or more. Every drop of water would be precious. You'd need to extract water from the air, from waste, from everything. The system would need to be incredibly efficient. But efficiency often means complexity, and complexity means more things that can break. One of the biggest challenges is removing carbon dioxide from the air. Humans breathe out carbon dioxide, and if it builds up, it can be deadly. On Earth, plants remove carbon dioxide, but on a comet, you'd need a mechanical system. The system would need to scrub the carbon dioxide from the air, then either store it or convert it back into oxygen. Converting it back into oxygen requires energy, and it's not 100% efficient. Some carbon would be lost. Over time, you'd need to replace it. This is why some researchers think you'd need to grow plants, even if it's just algae. Plants can remove carbon dioxide and produce oxygen, and they can also be a source of food. But growing plants in space is challenging. They need light, water, nutrients, and the right temperature. On a comet, all of these would be hard to provide. This would make your house complex. It would be more like a spaceship than a house. It would need to be self-contained. It would need to be reliable. It would need to be maintainable. But this is similar to what we've done before. The International Space Station is a complex structure. It has all these systems. It works in space. Maybe we could build something similar on a comet. The key is to start simple, to test ideas, to learn, to improve. Building on a comet would be a learning process. We would make mistakes. We would find problems. We would develop solutions. Over time, we would get better at it. And maybe, eventually,
we could build something that works, something that's comfortable, something that's safe, something that allows people to live on a comet. But it would take time, it would take effort, it would take resources, it would be a challenge. But it might be worth it. The possibilities are exciting. The future is unknown, but it's also full of potential. Chapter 5. Life on a Comet. What would it be like? Imagine waking up on a comet. What would it be like? What would you see? What would you feel? What would you do? Let's explore what life on a comet might really be like. First, let's think about what you would see. When you look out the window, you would see space. Black space, full of stars. But the stars would be different. They would be brighter. There would be more of them. Because there's no atmosphere to block the light, the stars would shine clearly. You would also see the comet itself. The surface would be dark, very dark, almost black. It would reflect very little light. But you might see features, hills, valleys, craters, boulders. The landscape would be strange, unfamiliar, like nothing on Earth. The surface would look like charcoal, but with strange shapes. You might see dunes made of dust, even though there's no wind. These dunes form because of the comet's weak gravity and rotation. You might see cracks that look like they were made by lightning, but they were actually made by the comet heating up and cooling down. The landscape would change every day as the comet rotates and different parts face the sun. It would be like living on a world that's constantly reshaping itself. If the comet was active, you might see jets, streams of gas and dust shooting out from the surface. They would glow in the sunlight. They would be beautiful, but they would also be dangerous. You would need to stay away from them. You would also see the sun, but it would look different depending on where the comet was in its orbit. When the comet is close to the sun would look bright and large. When the comet is far from the sun would look small and dim, like a bright star. At its closest point, the sun would look about twice as big as it does from Earth. But at its farthest point, the sun would look like just another star in the sky. You'd need a telescope to even see that it was the sun. The amount of light you'd receive would be tiny. A square foot of solar panel that produces 100 watts on Earth might only produce 0.01 watts when the comet is far from the sun. That's why nuclear power might be the only option for long-term survival. You might also see Earth, but it would be far away. It would look like a tiny blue dot. You would be able to see it, but it would be distant. You would be far from home. Now let's think about what you would feel. The first thing you would notice is the lack of gravity. You would be almost weightless. You would float. You would need to hold on to something to stay in place. Moving would be strange. A small push could send you flying. You would also feel the temperature. When the comet is far from the sun, it would be very cold. Minus 400 degrees Fahrenheit. That's incredibly cold. Your house would need to be heated. But when the comet is close to the sun, it would be warmer. The temperature would change dramatically as the comet orbits. You would also feel isolated. You would be far from Earth, far from other people. Communication would be delayed. You would be alone. This could be hard, but it could also be peaceful, quiet, calm. Now let's think about what you would do. Your daily routine would be different from life on Earth. You would need to maintain your house, check systems, make repairs, extract resources, grow food, do research, stay busy. You would need to be self-sufficient. You couldn't just go to the store. You would need to produce your own food, your own water, your own air. This would require work, but it would also be rewarding. Scientists have been testing ways to grow food in space for years. On the International Space Station, they've successfully grown lettuce, radishes, and even peppers. But growing food on a comet would be much harder. You'd need artificial light, since the sun would be too dim or too far away. You'd need to recycle every drop of water. You'd need to extract nutrients from the comet's organic molecules. Some researchers think you might need to grow food in sealed containers, using hydroponics, where plants grow in water instead of soil. It would be like having a tiny farm in your house, but one that's absolutely critical for your survival. You would also do scientific research. Comets are interesting. They preserve material from the early solar system. By studying comets, you could learn about how the solar system formed. You could make discoveries. You could contribute to science. You would also need to exercise. In low gravity, your muscles would weaken. Your bones would lose density. You would need to exercise to stay healthy. This would be part of your daily routine. Astronauts on the International Space Station exercise for about 2 hours every day. They use special machines that work in zero gravity. Even with all that exercise, astronauts still lose about 1 to 2% of their bone density per month in space. On a comet with even less gravity, you might need to exercise even more. Some scientists think you might need to exercise 3 to 4 hours a day just to stay healthy.
The effects of low gravity on the human body are serious. Scientists have been studying this for decades, and they've learned a lot. In space, without gravity pulling on your body, your muscles don't need to work as hard. They start to weaken. Your bones, which are constantly being rebuilt on Earth, start to lose mass. Your heart doesn't have to pump as hard, so it gets weaker. Even your balance system, which relies on gravity, starts to change. Astronauts who spend months in space can lose significant amounts of muscle and bone mass. Some of it comes back when they return to Earth, but not all of it. And the longer you're in space, the worse it gets. On a comet, with gravity that's 100,000 times weaker than Earth's, the effects would be even worse. You'd be almost completely weightless. Your muscles would weaken quickly. Your bones would lose density. You'd need to exercise constantly just to maintain some strength. But exercise in low gravity is challenging. You can't just lift weights because the weights would be weightless too. You'd need special equipment that creates resistance, like elastic bands or machines that pull on you. And you'd need to use it for hours every day. It would be exhausting, but necessary. Some researchers think you might need to create artificial gravity by spinning your habitat. But that adds complexity and cost. It's another challenge that would need to be solved. You would also need to maintain your mental health. Living on a comet would be isolating. You would need ways to stay connected, ways to stay busy, ways to stay sane. This would be important. Psychologists who study extreme isolation have found that people need several things to stay mentally healthy. They need social connection, even if it's just through delayed communication. They need a sense of purpose and meaningful work. They need routines and structure. They need ways to relax and have fun. On a comet, all of these would be challenging. The communication delays would make real-time conversation impossible. You'd be sending messages and waiting hours for replies. Your work would be critical for survival, which could be stressful. Your routines would be disrupted by the comet's irregular rotation and changing environment. And finding ways to relax would be difficult when you're constantly worried about survival.
Some researchers think that living on a comet might require psychological screening and training similar to what astronauts go through, but even more intense. You'd need to be someone who can handle extreme isolation, uncertainty, and stress. Not everyone could do it. But despite the challenges, life on a comet could also be amazing. You would be exploring, you would be discovering, you would be doing something that's never been done before. You would be a pioneer. You would see things that few people have seen. You would experience things that few people have experienced. You would be part of history, part of the future of space exploration. Life on a comet would be different. It would be challenging, but it could also be rewarding. It would be an adventure. It would be something special. Think about what it would be like to float in space, to see the stars, to be part of something bigger, to explore, to discover, to be a pioneer. Life on a comet would be unlike anything else. It would be unique. It would be special. And that's what makes it worth imagining. That's what makes it worth exploring. Chapter 6. The Future of Comet Exploration. What's next? Comets have fascinated humans for thousands of years. We've observed them, we've studied them, we've even visited them. But there's still so much we don't know, so much to discover, so much to explore.
In the future, we'll learn more about comets. We'll send more missions. We'll make more discoveries. We'll develop new technologies. We'll find new ways to explore. NASA and other space agencies are already planning new comet missions. The European Space Agency is planning a mission called Comet Interceptor, which will study a comet that's never been near the Sun before. This will help us understand what comets are like in their original state. Japan's Hayabusa 2 mission already brought back samples from an asteroid, which is similar to a comet. The samples contained water and organic molecules, just like comets. NASA is also planning missions to study comets and asteroids. And maybe, eventually, we'll build on comets. We'll live on them. We'll use them. Some scientists think that comets could be refueling stations for future space missions. If we can extract water from comets, we could make rocket fuel and support missions to Mars and beyond. One researcher calculated that a single comet could provide enough water to support thousands of space missions. That's why some people call comets cosmic gas stations. The Comet Interceptor mission is exciting because it will study a pristine comet, one that's never been near the Sun. Most comets we've studied have already made many trips around the Sun, losing material each time. But a pristine comet would be like a time capsule, preserving material from the very beginning of the solar system. The mission will launch in 2029 and wait in space for a suitable comet to come along. When one does, it will send 3 spacecraft to study it from different angles. This will give us our first look at what comets are really like before they've been changed by the Sun's heat. But studying comets is just the beginning. Some researchers think that in the future, we might be able to mine comets for resources. Comets contain water, which is incredibly valuable in space. They also contain organic molecules, which could be used to make materials or grow food. And they contain metals and other materials that could be useful. But mining a comet would be incredibly difficult. The low gravity, the fragile surface, the extreme temperatures all make it challenging. But if we could figure out how to do it, comets could become valuable resources for space exploration. They could provide water and fuel for missions to Mars and beyond. They could support long-term space settlements.
They could be the key to exploring the outer solar system. But we're not there yet. We still have a lot to learn about comets and a lot of technology to develop. While the idea of using comets as refueling stations sounds great, there are huge challenges to consider. First, you'd need to catch up to a comet, which is moving very fast. Then you'd need to land on it, which is incredibly difficult, as we've seen. Then you'd need to extract water, which requires a lot of energy. Then you'd need to process it into rocket fuel, which requires even more energy and equipment. And all of this would need to work in an environment with almost no gravity, extreme temperatures, and constant hazards. Some researchers think it might be easier to just bring fuel from Earth or to mine asteroids instead, which are easier to reach and more stable. But others think the challenge is worth it because comets have so much water. A single comet could have billions of tons of water. That's enough to support thousands of missions. The question is whether it's practical. Right now, it's not. But in the future, with better technology, it might be. That's why scientists keep studying comets. They want to understand them better, so that maybe one day we can use them. It's a long-term goal, but it's an exciting one. But that's in the future. For now, we're still learning. We're still discovering. We're still exploring. And that's exciting. That's what makes science interesting. There's always more to learn, always more to discover.
Comets are amazing objects. They're ancient, they're mysterious, they're beautiful, they're important. They tell us about the history of the solar system. They might have brought water and life to Earth. They're cosmic travelers, drifting through space, carrying secrets from the beginning of time. And as we learn more about them, we'll understand more about our place in the universe. We'll understand more about how the solar system formed. We'll understand more about how life began. We'll understand more about what's possible. The future is unknown, but it's also full of potential, full of possibilities, full of wonder. And that's what makes it worth exploring. That's what makes it worth imagining. So, can you build a house on a comet? Well, that's a complicated question. It depends on what you mean by building a house. It depends on what kind of comet you're talking about. It depends on where the comet is in its orbit. There are many challenges, but there are also possibilities. The challenges are real. They're significant. They would require new technologies, new materials, new approaches. But humans are good at solving problems. We've overcome challenges before. We've built things in space. We've lived in space. Maybe we could live on a comet too. The key is to understand the challenges, to plan for them, to develop solutions, to test them, to be prepared. Building on a comet would be difficult, but it might not be impossible. It would be an adventure. It would be a challenge. It would be something new. And that's what makes it interesting. That's what makes it worth exploring. The challenges are real, but so are the possibilities. The future is unknown, but it's also full of potential. Comets are fascinating. They're worth studying. They're worth exploring. And maybe one day they'll be worth building on, worth living on, worth calling home. But for now, we can imagine, we can dream, we can explore with our minds. And that's a good start. That's how great things begin, with imagination, with curiosity, with wonder. Think about comets. Think about their beauty. Think about their mystery. Think about their potential. Think about what might be possible. Think about the future and dream. Wow,
What a journey we've been on! We've explored what it would be like to build a house on a comet. We've learned about comets. We've discovered their secrets. We've imagined what might be possible. We've learned that comets are ancient travelers. They've been drifting through the solar system for billions of years. They're made of ice and rock. They're small, but they can have huge tails. They're dark, but they can be beautiful. We've learned about the challenges, the low gravity, the extreme temperatures, the lack of atmosphere, the radiation, the activity. All of these would make building on a comet difficult. But we've also learned about the possibilities, the water, the organic molecules, the scientific value, the potential. We've imagined what it would be like to live on a comet, to see the stars, to float in space, to be a pioneer, to explore, to discover. It would be challenging, but it could also be amazing. We've thought about the future, about what might be possible, about what we might discover, about what we might build. The future is unknown, but it's also full of potential. Comets are fascinating objects. They're worth studying, they're worth exploring, and maybe one day they'll be worth building on, worth living on, worth calling home. But for now, we can imagine, we can dream, we can explore with our minds, and that's a good start. That's how great things begin, with imagination, with curiosity, with wonder.
Science is full of questions, and that's what makes it awesome. There's always more to learn, more to discover, more to explore. The universe is vast and mysterious, and we're just beginning to understand it. Comets have been drifting through space for billions of years. They'll keep drifting for billions more. And we'll keep learning about them, discovering their secrets, and appreciating their beauty. They're cosmic travelers carrying secrets from the beginning of time. I'm Sleepy, and this was your science story for today. Sweet dreams, and keep looking up at the stars. Remember, every time you see a comet, you're seeing an ancient traveler drifting through space, carrying secrets from the beginning of the solar system. That's pretty special. Good night.